So let's look at page 5 of our week 3 concept check. Here we want to look at electron configurations and make sure we understand how each level of electron structure is represented and how we can utilize an electron configuration to tell us a lot of different information. One of the things that an electron configuration should tell us is the element that we're dealing with. Again, this is equal to the total number of electrons. And so to figure that out, all you have to do is add up your superscripts. And so in this case, I would go 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, 6 is 18, 20, 30. I've got 34 electrons total. I can go to the periodic table and I can see that that is element selenium, right? So again, the atomic number 34 tells me that I am dealing with selenium. Now, the other thing that we can look at, and you're going to see that I'm going to kind of erase each layer structure as we go through. So we'll kind of get rid of that work. Now we're going to look at shells. And for shells, what we want to do is remember that it is the number of our each subshell tells us what shell that subshell's in, right? So the 1s subshell is in the first shell, the 2s and the 2p are in the second shell, etc. And so to figure out how many shells you have, all you have to do is find your largest shell number. And so in this case, right, my largest shell number is 4. And so I can tell that I've got 4 shells that have electrons in them. And again, if we wanted to, we could break our 34 electrons down by shell, right? Because the first shell has just the 1s2, so it's got 2 electrons. The second shell has 2s2 and 2p6, so it has 8 electrons. The third shell here has 3s2, 3p6, and then it's got the 3d10, so it's got 18 electrons. And then we have the fourth shell with 4s2 and 4p4 with 6. And so there's our 34 electrons broken down by shell. Now, when it comes to subshells, what we want to do is we want to count the number of what I would call terms. Right? Each term is a subshell. So 1s, 2p, 3d, etc. Right? Those are terms. And so in this case, if we count terms, right, we've got 1s as a term, 2s as a term, 2p. Going to make my circles or my highlights just a little smaller. So again, 1s is a term, 2s is a term, 2p, 3s, 3p, 4s, 3d, 4p. And so I've got 1, 2, 3, 4, 5, 6, 7, 8 terms, or 8 subshells accounted for in this particular electron configuration for selenium. Now, when it comes to orbitals, which is our next category, orbitals, to figure that out, you need to count boxes with an arrow. That would be my recommendation. And of course, what that means is you need to fill out an orbital box diagram. And so remember that to fill out an orbital box diagram, we just count to 34. We just count the way that we talked about on the previous page. So again, I go 1 up, 2 down, 3 up, 4 down, 5, 6, 7 up, 8, 9, 10 down, 11 and 12 up, down, 13, 14, 15 up, 16, 17, 18 down. That's 3p6. There's my 4s2. Remember that I know my 3d is full, so I've got my 5 up. Then I come back 6 through 10 down. So there's 30. And when you get to 4p, remember Hund's rule. So those 4 electrons go in 1 up in each, and then the 4th one comes back in pairs. And so what that means is when you go to count your boxes, you're going to have 1, 2. Remember, these are 3 boxes, 3 orbitals here in the 2p. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and now 16, 17, 18. So we've got 18 orbitals, 18 boxes that have 1 arrow. And so because of Hund's rule, it may not always work out that you have 2 electrons per orbital, right? We've got 34 electrons total. We would expect 17 orbitals if we put 2 electrons into each. But because we end in a subshell with multiple orbitals, and because of Hund's rule that puts 1 electron in each of those orbitals first, we end up with an extra, if you will, orbital because we have 2 orbitals with only 1 electron in them. And then there's all sorts of other things I could ask about a specific layer structure. So in this case, I've asked about just the 3rd shell. And so if we want to find things just in the 3rd shell, again, what we're going to do is we're going to go in and we're going to find our terms that have a 3 in them. So I've got 3s2, 3p6, 3d10, and then what I want to do is I want to add up those those superscripts. So the 2, the 6, and the 10 add up to 18 electrons in the 3rd shell. It's just a coincidence that my last 2 numbers there are the same. Now, let's look at our second example. So here, we stop at 3d3. We're going to do the same thing that we did before. So for our first question, we're going to add up our superscripts. So 2 plus 2 is 4, 6 is 10, 12, 18, 20, 23. We've got 23 electrons. And so I can go to the periodic table and see that we are dealing with vanadium. In terms of our shell number, right, I've got the first shell, second shell, third shell, and then there's the fourth shell. Be careful, it's not the last term because we go back into the 3D after we've gone out to the 4s. And so vanadium is also going to have 4 shells with at least 1 electron. Remember that this should also be the period that the element is in. And so vanadium is in the 4th period, the 4th row down in the periodic table. Now, in terms of subshells, what we want to do is we want to, again, count our terms. And so, in this case, we've got the 1s, the 2s, the 2p, the 3s, the 3p, the 4s, the 3d. So I don't have the 4p, so I've got 1 less than I had before, right? And so I had 8 subshells in selenium. Now I only have 7 subshells here represented in this configuration for vanadium. For orbitals, again, I'm going to want to go in and do my orbital box diagram. And so I'm counting to 23. And so again, make sure you do 7 up, 9, 10, 11 down, 12. Then we go through 3p. 4s has its 2. And then we get to 3d, because of Hund's rule, we put our 3d electrons into 3 separate orbitals. And so when we go to count our boxes, again, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 orbitals represented for vanadium. And then another question that I could ask is, how many electrons are in p orbitals? So instead of looking for a specific number, shell number like we did in our last question of the previous one, here we're looking for anything that's a p. And so we've got the 2p and we've got the 3p. We've got 6 electrons in each for a total of 12 electrons in p orbitals for this particular electron configuration. So again, hopefully this helps you kind of go full circle with all the things we've been talking about and start to and really feel comfortable with what's the shell, what's the subshell, what's the orbital, and how does an electron configuration account for all those. Thank you so much for all your time going through this concept check with me. Have a great rest of your day.